by this formula where this takes into account the interaction. This is the normalization condition, and nu is the filling factor. And then, if I have zero temperature, the solution of for the occupation numbers is more or less like the thermospheric regime in PECs. Energy smaller than the chemical potential, it's larger than chemical potential, it's zero. Yes. Then I get a critical value of the interaction strength for delocalization, and the answer is also valid for temperatures much smaller than the distance between the clusters. Again, this omega is the distance between the clusters. Yes. Now, what I can do, I can continue and consider finite temperatures where temperature is larger than the distance between the clusters. Assuming that the occupation numbers are large, I get an algebraic formula for the occupation number. And then I obtain a critical value of the interaction strength. So far, so good. But what is interesting here, that what you see from this formula is that I increase temperature, and then the interaction strength, which is needed for delocalization, becomes larger. This is counterintuitive, because what we were actually saying for ordinary outer cold bosons is that when the system becomes hotter, it's easier to delocalize the system. And here it's the other way around. I warm the system, and then I get to the insulating state. Yes? So, I can give you an example. Take a glass of water, let's assume that this is a glass of water, and then you heat it up. And then what we expect is that either we get a hot water or a water vapor. Here, the answer is the opposite. You get a piece of ice. You heat up a glass of water and get a piece of ice. Why? The reason is, and actually before I go, let me show you the graph. At low temperature, I start in the fluid phase. I increase temperature, and then I arrive at the insulated state. And different colors are related to different values of the filling factor in the entry gradients. Why is that? Look at the density of states. The thing is that, as I already told you, the criterion for delocalization contains density of states in the square. Yes. Here, the density of states here is much larger than here, and therefore, only particles from this cluster, from the lowest energy cluster, participate in the delocalization transition. Now, at zero temperature, everybody is sitting here, and everything is perfect. When I increase the temperature, then part of my particles goes from here to here, to here to here. The number of particles in the cluster which participates in the transition becomes smaller. Therefore, the interaction strength which is needed for delocalization becomes larger. It's as simple as that. And that's what you see here. Right. People were first telling us, and first of all, Allider, that this can be an artifact that you took the limiting case, that the shallow list has a much larger period, and so on. What we have done then, we have considered the so-called golden ratio, when the ratio of periods is square root of 5 minus 1 divided by 2. Do not ask me why this is called golden ratio. Yes, these are mathematicians who said that for this ratio of the period, the system minutes best of all the disorder. And then, for this particular case, we also see this behavior. And all results which I am showing you have been obtained by using exact diagonalization for a single particle project. That's what it is. So we call it anomalous freezing with heating behavior. Sounds funny, yes, and this image with the glass of water I'm usually giving when I give a public lecture. Sorry for that, but it's quite funny. And then what I see now here is that our chairman becomes a little bit nervous, yes, which means that I have to stop my conversation with you. Yes. So what I'm going to say is that one-dimensional models is a promising system to study the many-body localization, delocalization, transition. Yes, and that's what you are aiming at the moment. And atoms and quasi-periodic potential. You have increasing temperature may favor localization. And thank you for attention. Questions?
I'm going to ask a very naive question. I'm going to ask a very naive question. In quasi-periodic potential, in periodic potential, we know how to classify eigenstates, eigenenergies. Bloch theorem holds. But how to perform calculations in quasi-periodic potential compared with periodic potential?
What you can do, you may introduce a certain length of the system. Yes, let's assume that it is sufficiently large. Then put this quasi-periodic potential on this length scale. Yes, and let us assume that we more or less know that if the states are localized, what is the localization length? We more or less know from theory of André Aubry and so on. And we take the length of the system much larger than this localization length. And then what you do, you may do the exact diagonalization of the Hamiltonian and exactly obtain numerically the eigenstates. This is what we have done, and Saint-Michel did it for the various types of length scales in the system. Yes, this is possible to do. Yes. And people have done that, including some analytics before and so on. This structure of clusters has been first obtained quasi-analytically by Suslov. Then other people reproduced it also analytically or by doing numerics. Yes, and so on. That's what we have also done. So the answer is that there is a lot of analytics, but what you can do, and even for a large system, you may do exact diagonalization to find the spectrum. Yes.
In this case, we truncate the system. For a periodic potential, we can handle the infinite, an infinite system, right?
Yes.
But in quasi-periodic case, we need to first truncate it to a finite system.
This is true. This is true. But then, what happens is that using exact diagonalization in the single particle problem, you may have 100 particles, 200 particles. That's what you can do. Yes. For single particle problem, if you have to solve an interacting particle problem by exact diagonalization, this is much more difficult. But for a single particle, you may just do it when the system is larger by the localization length by a factor of 10, 5. Depends on the calculation.
If localization happens, you don't care for regions very far from the localization region. Yeah?
You do, because what happens is you may take the initial size of the system, which is by a factor of 10 larger than the expected localization length. Expected localization length again, and then obtain wave functions. Then you obtain wave function, which is centered here, localized wave function, centered here, localized, centered here, localized, and so on. That's what you obtain. That's what it is.
Thank you.
Yeah, I'm curious about how would you see the difference between these two phases in the transition as a function of temperature from the solid phase to the localized phase. going to the insulated.
So, do I understand correctly that the question is how do I distinguish between the insulated?
What are the big experiments?
Like in a medium.
Ah,
Yeah.
you know, the thing is that the simplest answer to this question is, imagine please, that you have a system which is confined by an external potential. Yes? Then, yes, it's a very, thank you, Charles. Then, what happens is that if you then switch off the confinement and the system is in the extended state, it expands, yes? If the system is in the localized state, then it cannot expand by more than part of the localization, just a little bit, and the expansion stops, yes? This is the simplest thing to do, and people know that. Let's say thing number one, that's how the Anderson localization has been first identified in the first experiments by Elena Speer and by Massimo and Gruccio. Yes. Very nice guys. Yes. They even have published their works one after the other in Nature. Yes.
But one concern with this is that you can have, in your random potential, you can have like perhaps some points where you have some very high barriers. And this might take a long time to overcome. So of course you're doing expansion, but you also have a finite time to look at the system, right? Experimentally. It would decay or whatever. So can they really tell the difference between real localization and just the fact that the system is blocked by a...
The thing is that what you can also do, you may address the momentum distribution of particles, yes? And this is what Giovanni Modugno and his people have done in the last experiment, yes? And then you may address the momentum distribution, which distinguishes in between localized and delocalized states. That's what they can also do. I'm not able to explain the experimental technique in detail, but that's what they can do. They now know how to do it. So, the first thing that I have told you is very simple. And what they have done, in order to prevent them from having extremely high and wide peaks, they just made, on average, the amplitude of the disorder potential very small. And that's why, therefore, what they did not mean. In the very first experiment, this was just the origin of what they have seen, but not anymore later on.
There's a lot of numerical studies on speed chains, and so at small magnetizations, spin chains should look pretty much like bosons. Let's say if SZ is conservative, like particle conservation. So mostly people study, let's say, zero magnetization or just average over all magnetizations, and then transitions. The transition to MBL does not depend on temperature. It's just like the entire spectrum goes from being localized to being localized. So, well, the first question is, can you actually make connection to a lot of numerical studies on spin systems? And second, can you make predictions that say, if people were to do this at very small polarization, they should see a very different behavior?
The thing is that large part of the research that you are talking about is related to the so-called infinite temperature case.
Well, that means averaging of the entire spectrum.
Here, just a second, let me answer. This is one of the limiting cases in our calculation. And when we have done the calculation for this Andreev-Harper model, we also considered the case when temperature is tending to infinity. Yes. And we nicely reproduce interesting results and so on. What you are talking about is this activity of all these numerical people, which is quite limited because of their numerical facilities. This is Hughes and all these guys around. We recently had a workshop at Santa Barbara where all these people were present. Yes, and we had a lot of discussions with them. But, you know, this we easily reproduce from our calculations, for example, for the Andreev-Bree lattice as the case of temperature tending to infinity. Absolutely no problem. Then, they have also done some work for fermions, yes, and what we, at an infinite temperature. For us, it's a small exercise to consider these fermions from bosons and then introduce infinite temperature in the calculations. We reproduce the results. No problem.
I think it would be interesting to focus on things where you can contrast, like your prediction on what is commonly known about those numerals.
Of course, it is quite interesting to indicate these people where and why they are wrong. Yes?
I'm not sure that
Well, I'm not sure either, but you know, so far they have considering many-body delocalization transition as a finite temperature phenomenon. What they have done, they have considered very little things. The case of infinite temperature. Yes.
I don't agree. You can look at the entire spectrum and see that it doesn't matter which part of the spectrum you take.
Zheng, we looked very carefully at what they have done. There was some numerical work which was trying to address the finite temperature case. Yes. But mostly what is done when they do it for the entire spectrum, yes, as a whole, it's infinite temperature case. Yes. Ask Vadim Oganisyan and he will agree with this statement. Yes. Okay, that's fine. But what do you want me to say? Do you want me to indicate the case? So far, I was not interested in indicating these people where they are wrong. I can, if they insist, yes? But, you know, so far, what I was mostly interested in is to predict new interesting phenomena, not saying that some numerics was not good somewhere and so on. This is what I was not yet interested in. If you insist, I can.
Sure. I have a question regarding the experiments we are talking about with one-side potentials. So in principle, that means at least this kind of experiment can be done at finite temperature, right? And also with disorder and something.
Yes.
Why can?
Yes. Let me explain you something which I didn't do during the talk because I was seriously worried about the time. Yes. The thing is that in the experiment that I showed you, again this microphone problem, is there a technician who is responsible for these microphones and so on?
We should point to you.
Okay, good, good. So I should always keep the microphone and my mouth in a proper position. If the technician is here, show the guy to me, I will seriously punish him for that. Yes. And the thing is that in the experiment that I showed you, where they have identified, you know, I'm cold and I propagate the infection, the next speaker will get the infection. Be aware of that. So, the thing is that in this very nice experiment where they have measured insulator fluid transition, they had a difficulty to control temperature. The temperature in the experiment was known, let's say, within factor 2 or 3 only, or even factor 4. They still have this temperature problem in the experiment, but they are trying to solve this problem. Therefore, what they said in their work, that after they have done, and there were theoreticians jumping around this experiment. Theoreticians were including one good guy, this is Thierry Giamarchi, yes? And then what has been done is that they said, okay, if we attribute our results of the experiment to 0 temperature, everything is more or less okay. But, you know, we especially had several discussions with these experimental people, And already for quite some time they have a problem to control temperature in the experiment. It is quite likely that now they are trying to solve this problem. And they will solve it, but it probably will take a little bit of time. Yes.
So is there any more questions? So, okay, if not, let's thank Jorah. So we are going to have tea time, and